Okay, in the last video, we built up the idea of individual convection cells, three in the northern hemisphere, three in the southern hemisphere, right? These Hadley cells that are north and south of the equator, followed by the Ferrel cells, and then the polar cells. Okay, and they convect in opposing directions, as indicated by those arrows at the left. But generally speaking, they're characterized by warm air rising and cool air sinking, right? And so warm air rises because it's less dense, but it also holds more moisture than cooler air. Okay, and so let's just leave those colored arrows there to indicate the temperature, and let's go ahead and replace those with the dominant wind patterns, the trade winds around the equator, north and south, and then the westerlies up at 45 degrees north and south, and the polar easterlies up north and down south of that. And so those are the general circulation patterns, and the arrows there indicate the temperature. But as we said, warmer air can hold more moisture than colder air. Okay, and so as warm air traverses the Earth's surface, it drives evaporation, picks up moisture as it warms. Okay, and then when it begins to rise in the atmosphere, it starts to cool off that air. The air starts to cool off, right? Remember, it's colder up at altitude than it is down at the Earth's surface because the source of the warmth is infrared radiation that's being emitted by the planet's surface, right? Sorry about the weird connection there. It's stuck green now. Okay, and so there's snow on the San Gabriels right now because it's cooler up there, right? It was almost 80 degrees yesterday in Claremont. There's still snow in the mountains because it's cold at altitude, right? And so when air rises away from the Earth's surface, like is the case at the intertropical convergence zone down near the equator, when that warm air that has been traversing the Earth's surface, absorbing moisture, when it rises and it cools off, the moisture condenses and it rains, right? It precipitates out of the air. And so if we look at the slide to the bottom right, you can see that there are clouds indicated around the intertropical convergence zone. There's also clouds up here at this other convergence zone around 60 degrees north and south latitude. And so you end up getting some precipitation up there, but mostly, right, we think about the equatorial or intertropical regions as being characterized by rainforests. Okay, and this is why. Right? There's a lot of rain in the subtropics because warm air is rising in the atmosphere and its ability to hold moisture is decreasing as it cools off. That moisture has no other option but to precipitate out and form rain. Okay, and so this makes a prediction about the distribution of vegetation essentially on the Earth's surface. We would expect to find rainforests around the equator, and we do, right? It also makes another prediction. Because up at 30 degrees north and south latitude, if you look at what's happening, you have cold air that's been traversing the upper atmosphere, right? It's been coming from equatorial regions, it's been coming from higher latitude regions in both directions, and it's getting colder and colder as it moves through the upper atmosphere. As a result, its ability to hold moisture goes down and down and down, further and further, and pretty soon, as it moves away from equatorial or subtropical regions, it doesn't have any moisture left. And so when it comes back down to the Earth's surface and it warms up, its ability to hold moisture goes up, but it doesn't have any. And so it just absorbs any moisture that it can. Okay, and so as a result, it doesn't rain at 30 degrees north and south latitude, generally speaking. Those are characterized by high pressure systems where there's cold upper atmosphere air coming down to the surface and driving evaporation as it warms up. Okay, and so we expect precipitation in the subtropics, and we expect no precipitation or very little precipitation around 30 degrees, both north and south. And that's a direct result of these convection cells, okay? But it makes a really important prediction about the distribution of vegetation on the Earth's surface, right? It assumes that it's going to look something like this. We're going to have lots of vegetation down in the tropics, and we're going to have lots of deserts around 30 degrees north and south latitude. And if we think about that, that is indeed the case, right? We have the Sahara Desert in northern Africa, right in this region. I'm not in the right layer. But we have the Sahara Desert. Southern Africa is also very arid. South Africa is a desert. Namibia is a desert. But in between, we have the Congo, right? A giant rainforest. Similarly, in South America, we have the Amazon in equatorial subtropical regions, but down further south, it's pretty arid. In fact, the driest place on Earth, or one of the driest places on Earth, is the Atacama Desert, which is in the high Andes Mountains, right down here around 30 degrees south. We also have, the Arabian Peninsula and the Gobi Desert further over into Eastern Asia. But in general, at the first order, it makes a really strong prediction, and that prediction is true, right? And so this is how atmospheric circulation drives climate, through warm air being less dense and holding more moisture than colder air. That controls circulation patterns and precipitation patterns both.